Okay, thanks everybody. I appreciate the opportunity to come here and visit with you today and talk a bit about the, I guess this topic, bioenergy in forests. I'll focus a lot on supply of biomass material, where it may come from and how it interacts with, carbon and carbon storage. So following up on a lot of points that others have raised and trying to maybe emphasize a few alternative views related to some of those. The outline I'll take today is I'll talk first about sort of forests as a stock resource, and I think it's important to focus there and think about that as we think about what the implications of supplying biomass material from forests would be, and how that interacts with those natural climate solutions, which I'll oftentimes refer to as just forest carbon storage.
I'm sorry, Brent, were you going to be sharing slides?
Yep, they're not sharing yet.
No, not yet.
Not yet.
There we go. Are those working now?
Perfect.
Yes.
Okay, great. Thanks. Sorry about that, folks. So yeah, I'll be sort of working through this outline here. That I guess the second point that I want to talk about past sort of forests as a stock resource is that talk through sort of what factors affect the supply of wood and the storage of carbon in those forests, talking about some regional differences and similarities, as well as what I think are really important things to consider, which is long run and short run implications. Finally, talk a bit about how do carbon sequestration program and a biomass energy program affect wood supply and carbon storage together. I mean, are these things complements or are they substitutes in the short run, long run, and at different sort of carbon prices? For most of this analysis, I'll be using results from our global timber model. This was a model developed originally by Roger Sedgwick and Ken Lyon in the 1980s. I've sort of taken on the work with that in the 1990s and continued to develop it with a number of other colleagues. A lot of the results here will come from this paper by Alice Favero and myself and Adam Degno that appeared in 2020. Just a couple definitions here. I'll be talking about sort of high and low demand for biomass and bioenergy. And when I refer to high demand, I'll be thinking of these sort of RCP, representative concentration pathways. So a high demand scenario would be sort of an RCP 1.9, which would obviously be shooting for a world where we have less than 1.5 degrees of temperature change, sort of a Paris Agreement type world. RCP 6.0 would obviously be a lot lower level of ambition by the global community, so it's lower biomass demand. And of course, the carbon prices to do either the biomass demand or the demand for carbon in forests would be lower with the RCP 6.0 than they would be with the RCP 1.9. So just keep that in mind. When I refer to low demand, I'm sort of thinking of an RCP 4.5, 1.9, or 4.5 or 6.0. Thinking of high demand is sort of an RCP 1.9. So thinking of forests as a stock, it's important to recognize that forests are a really big stock of biomass and carbon. They're age dependent, so older forests do grow more slowly, and this has a big impact on our observation of annual fluxes of carbon rather than necessarily the carbon stock. It's important to keep in mind that annual harvests are relatively small. They're a small proportion of the stock. So here's some numbers from our global timber model. We have an above ground carbon stock, which is pretty consistent with what FAO has. Some of our data is derived from FAO, but most of the data from nearly all the temperate countries and boreal countries is derived from the national forest inventories that individual countries have collected. So we have 258 gigatons of carbon stored in forests in stocks, and just the above ground stock, just to sort of focus on that number for now. The annual harvest of carbon is about, leads to a release of about 0.6 gigatons of carbon. So I've denoted that as a positive there, just to denote the fact that that goes into the atmosphere. It's a really small proportion of the 258, it's only about 0.2%. Net deforestation is about 1.5 gigatons of carbon, it's about 0.6%. Annual growth, which is the sort of gross growth of carbon in forests, is a negative 2.3 gigatons of carbon, about 0.9%. So it's still relatively small, but bigger than those emissions of harvesting and net deforestation. So we have a net growth of carbon in forests annually of about negative of about 0.2. So we're taking carbon out of the atmosphere and putting it into the forest stock. This isn't, this is well understood in the literature. Obviously, the Global Carbon Project has similar numbers when they use the dynamic global vegetation models, and they predict that there's about a 1 billion ton or 1 gigaton net movement of carbon from the atmosphere into the forest. This is not a new process. This has not just happened recently. What we know when we look back in time is that there's been a large emission of carbon from deforestation and from use of forests over time. But since about the 1950s, the gross sequestration of carbon in forests has exceeded the net emission or the gross emission, so that the net effect is a movement of carbon on net from the atmosphere into forests. So we can look at this across regions and kind of think about where it is. And again, these are estimates from our model, the global timber model, looking from the present into the future. And we project that a significant portion of this occurs in the temperate zone, a big portion of it in the US, but pretty much spread across the countries, almost in direct proportion to the area of forest those countries have, with the exception of Canada, which has relatively modest fluxes at present. There's a negative flux, that is a movement from the forest into the atmosphere. I do apologize for flipping these numbers around here relative to the earlier one. I should have been thinking about that when I put this together. But the negative numbers here do mean an emission into the atmosphere. So the tropics in our model are an emission into the atmosphere on net, accounting for both. Our model actually does account for carbon fertilization and other climate processes in it. So we do find that the net effect of those things is a movement of carbon out of the atmosphere and into forests, with a flux of carbon from forests to the atmosphere in gross or in total from the tropics. However, our model also shows a reduction in deforestation over time. And so we see that the tropics become a bigger sink in the future, as do the temperate zone. So we kind of predict in our model into the future something very similar to the past. That is, we continue to become a stronger sink in forests around the world as we move into the future, accounting for carbon fertilization and other climatic processes. So one of the underappreciated things, components of these changes, is really, in my mind, this component of forest management. So the nice thing of having a model like this, we're able to actually disentangle the effects of different components of what affects the carbon system. And based on our model, we've estimated that carbon fertilization and climate change account for about 40 to 50% of the net sink. Forest management, 10 to 20%, and sort of forest aging or forest regrowth as a result of land abandonment, the other 20 to 30%. And that's just on the positive side. Of course, the deforestation is an anthropogenic thing that's affecting those forests on the negative side. So an unappreciated component, and I think it's important for us to think about when we start considering whether or not biomass energy and demand for biomass energy would be a carbon neutral thing or not, is this role of forest management, which has on net had a positive effect on the carbon balance in forests in the last century, and we're predicting it to have a positive effect, and even stronger effect into the future. So what affects the supply of wood and biomass? I think of four different things. First off, planting and managing forests is really, really important. Compared to natural regeneration, planted and managed forests can increase biomass by 2 to 3 times. We can do this by looking at estimates from the US FIA data, which pretty clearly indicate that planting forests in the South and other parts of the countries have had a pretty massive impact on the amount of carbon that's stored on any given site. The share of planted forest continues to increase as well. There are about 300 million hectares of planted forest globally, and 90 to 120 million hectares of those, depending on whose estimates you believe, the most are commercially active, that is used for industrial forestry. That accounts for greater than 50% of our industrial wood harvest. Another important component on the supply of wood and biomass is going to be access. Wood is harvested from inaccessible forests where value is greater than marginal access cost. So, this is actually one component of, starting to understand why there could be a difference between, say, the types of models that John Gunn showed with respect to how biomass demand affects, carbon neutrality, and this model shows how biomass demand affects carbon neutrality. In our model, harvesting in parts of the Northeast, if it's occurring in the baseline in the business as usual, that would basically be carbon neutral because most of that harvesting is for conventional wood products. When there's an increase in demand as a result of, say, a bioenergy project, that increase in demand will raise prices and will induce people who wouldn't have otherwise harvested to then harvest their trees. Our results would also show that in that particular location where that happens, that's a carbon negative activity, that leads to a net release of carbon into the atmosphere. What our model would also show is that that increase in prices leads to investments and increases in carbon in other places that typically more than offset the losses that happened in this inaccessible region. So it's important to keep this access cost in mind, that it does have an important implications for what happens with respect to carbon neutrality when prices rise or fall in timber markets. Forest types has an important impact or implication for the supply of wooded biomass and biomass. There are relatively few species per hectare actually commercially viable in the tropics, at least with traditional timber markets, that is using things for songwood type purposes. The dipterocarp forests in Southeast Asia are don't fit that example, because many more dipterocarps can be used for traditional songwood uses. However, we've noticed a massive movement of species around the globe, for timber production purposes. And Brazil is a fantastic example, because they moved eucalypts back in the 1800s, from Australia to Brazil, and it's now kind of, there's 14 million hectares or something like that in Brazil of these eucalypt plantations, which are actually feeding. You could think of it as kind of like a biomass type system, because they're feeding charcoal into the production of iron. So you could kind of think of that as somewhat of as a sustainable iron ore system. So, we move species around the world in order to sort of meet the needs for the wood producing sector. Climate and climate change has been mentioned many times, are having both positive and negative feedbacks, but seem to be having more of a positive effect right now. Carbon fertilization seems to be stronger in lower latitudes, and these dieback processes seem to be larger in the higher latitudes. So where and when can wood supply be increased to meet future biomass energy / BECCS demand? So it's important to think about the difference between the short run and the long run. When we perturb our model with high demand for biomass energy, what we find is that the tropical region is actually fairly elastic in the short run. That is, in the next 20 to 30 years, we can get up to a 14% increase in supply. And that would be with the sort of RCP 1.9, a really high demand for biomass energy. The temperate region actually has really limited capacity to expand supply in the short run. We find only a 3% increase in supply is possible in the short run. And if you think about it, that's just mainly due to the opportunity cost of shifting from shorter rotations to longer rotations. It's really expensive to shift rotations around in forestry and existing forests. People have plans with those existing forests. Interest rates that landowners have are 6 to 8 to maybe 10%. It's pretty expensive to then try to shift that rotation age from either a longer to a shorter rotation age, or from a shorter to a longer rotation age. And that really limits our ability to shift supply, because we can't instantaneously grow 30-year-old trees. We have to invest in those 30-year-old trees to get them. So it takes some time to build supply in the temperate region. On the other hand, the tropical regions, we have shorter rotations with the trees we do plant, and there is a fairly large amount of inaccessible wood that could be potentially harvested. In the long run, though, both regions can substantially expand supply by up to 30 to 90%. So we can see pretty significant increases in supply over the long run. Regions that have a longer land base and currently rely more heavily on plantations are best able to expand output over time. So to get a sense for where this happens sort of spatially, I apologize for not being the greatest mapper at putting this all. I know this would be better in a map, so I do apologize for this, but the best I could do personally is a table. I'm not the best mapper. But what you can see from the table is this idea that you can, in the short run, get only up to a 3% increase on average in biomass supply from the temperate zones. That's pretty spread evenly across the temperate zones. Japan gets a pretty significant increase in investments, not so much land area in forests in Japan. That leads to an increase in supply in the short run relatively quickly there. In the longer run, in the temperate zones, we get pretty significant increases, with the US sort of leading the way here, but other regions getting significant increases in supply as well. The tropics get a slightly bigger. This is kind of at the maximum with a really high demand scenario. They have a bigger increase in demand or in supply, a 14 to 21% increase in Central America, 30% increase in Africa and the Middle East, which isn't a big change in quantity, but it's a big change for that particular region. Over the longer run, obviously, they can increase that even more. So, what we see is really in the future with biomass expanding, we see almost more of the same, because these percentages are similar across the regions. We don't see the tropical regions sort of outpacing the temperate regions. We see much of the increase in biomass under the high demand scenarios occurring in temperate zones. So a lot of what we see in forestry is that where forestry has been successful at producing more wood, we see more investment, a doubling down in investment in those same kinds of technologies to increase more wood in the future. There are some costs to expanding biomass. Energy supply, one of those is that the timber supply falls, that is the production of trees for songwood, typical songwood uses declines. So prices rise, we get up to 150% to 300% increases in timber prices. So the timber sector loses consumer surplus, experiences significantly higher prices because we do convert both pulpwood and songwood into biomass uses in the future, given these sort of high RCPs, or these RCPs that try to achieve fairly low temperature increases in the future. Natural forest losses increase. We get 1 to 2% increases, increased losses in natural forests. So a consequence of increasing bioenergy supply is that we do lose natural forests. I think this is consistent with many of the results that Steve Rose showed earlier from some of the large integrated assessment models. Management intensifies a lot. So our model shows that people plant more trees and they intensify the management of those planted trees. That is, they're either fertilizing them more intensively to get more growth out of them. They're more successfully working to tamp down competition with other types of things, especially at the beginning of a timber rotation when trees are susceptible to competition from weeds and other kinds of plants that actually can grow faster than those trees, et cetera, et cetera. So management intensifies significantly as a result of an increase in biomass energy supply. So how does biomass demand affect carbon? In our model, in almost all cases, on net, it results in an increase in carbon. And the reason for that is largely because with an increase in demand, especially with these RCP scenarios, which show an increasing amount of demand over time, right? If we were to instantaneously increase demand today, then we would show some net fluxes of carbon to the atmosphere and potentially a negative effect of biomass energy. But because we don't expect BECCS or biomass energy to instantaneously ramp up, but to ramp up over time, the forest sector has time to anticipate that, has time to prepare for that, and has time to start to manage for that future in which more wood is demanded. So we can see here in the 4.5 watt per meter, sort of RCP 4.5, we can see that, that initially actually we have a slight, so the line we want to follow here is this one, is the difference between the baseline and the RCP scenario. And this suggests that there's a slight emission initially in the 4.5 scenario, and that over time, more carbon is stored in forests in the 4.5 watts per meter scenario than in the baseline. If we go to a really strong RCP, the 1.9, we see that in fact, actually, in the near term, there's no change in carbon, and in the long term, there's a significant increase in carbon stored in forests. So the idea here is that biomass energy demand actually strengthens the carbon sink, especially over a long time, and carbon debt is a reality in some locations. We can actually see it here. This is carbon debt, right? It happens in some time periods or in some particular locations, but it's typically outweighed by other changes that occur in the biomass supply system across time and across space. This just takes those results and shows some of those results in the, I have my own timer here, so I know I'm getting close to my 20 minutes. I should have about 1 minute left, which I think is almost perfect for the slides I have.
Yes.
The carbon outcomes resulting from this biomass expansion program are pretty modest changes in the short run, and slightly bigger changes in the long run, but still pretty modest changes in carbon. So this is saying that we can dramatically increase wood supply in the long run and not have a massive effect on the supply of carbon in forests. But recall, there's a big effect on timber prices. There's a big effect on natural forests. So there are costs to this policy. It's not a free lunch. Final question is, does a carbon sequestration program reduce the supply of biomass? So what if we add to this system of increasing biomass demand? What if we add to this system a program that tries to foster and support carbon storage in forests through natural climate solution type programs and processes? And what we find here is that it actually does become really difficult at high levels of demand, that is at these RCP 1.9. Basically, this line down here is showing that it becomes very difficult to both maintain carbon in forests and increase the supply of wood. So what happens is we actually, in an RCP 1.9 scenario, we actually reduce the amount of total wood supply, both in the short run and the long run, in favor of storing it in forest in natural climate solutions. The concept here is that when we then go out to value the stock of carbon in forests, so we're valuing the stock of carbon in forests and we're paying for it, and we're valuing the stock when used for bioenergy, it turns out that the value of the stock in forests is actually stronger than the value of carbon and the value of using that material for bioenergy, at least along the scenarios we looked at. So it turns out that you would actually make the decision to store more in forest if you had a valid carbon sequestration program in forest and not convert it all into biomass energy. So for the folks who are looking for a way to sort of maintain carbon stocks in the long run, there's really no substitute for a system that values natural climate solutions and actually pays for them. This shows where that happens. I'm not going to go into too much detail about that, but it kind of shows where the changes in biomass supply happen as a result of a carbon sequestration program that's sort of layered on top of the biomass program. And you can see it's pretty consistent across the regions. There's a pretty large reduction in the supply of wood material. So the conclusion is that over the last century, we've switched from our forest management from an old growth harvesting to a renewable management system. We really have. We've moved from an old growth harvesting to a renewable management system. And as a result, since the middle of the 20th century, wood supply has grown to meet demand. Literally, our system of harvesting trees now is that we plant trees in order to harvest them, and we plant as many trees practically as we actually harvest, or I should say in terms of stock. Right? This trend is expected to continue even with high biomass demand, allowing our forests to remain a carbon sink. High biomass demand does cause a large change to forests. There's less natural forests, there's more plantations, but more carbon sequestered. Our results suggest that, while there could be some really negative consequences of a biomass energy program for forests, less carbon is not one of those negative consequences, because we see globally that there would be more carbon. Due to the nature of forests and forest management, namely high opportunity costs and high access costs, there's very limited short-term ability to increase supply. That's why we can see a carbon debt happen, because the increase in supply in one region does mean there's an over harvest in that region. And finally, the incentives to store carbon on the landscape with carbon sequestration programs are stronger than the incentives to harvest wood, as ambition to reduce net carbon emissions increases. So as we start to move towards these sort of Paris Accord agreements, our model results suggest that there's a really strong incentive to maintain carbon in forests rather than allowing it to be harvested either for traditional wood product markets or for biomass energy markets. So with that, I'll end up. I think we're opening up for everybody now.